I'm with the Barnes Group Advisors, where our mission is the industrialization of additive manufacturing. A little bit more about me, my background. I started at Honeywell Aerospace in Phoenix, working in metal AM there, qualifying parts with the FAA on laser powder bed additive machines. And then I went on to work at Alcoa and do much of the same, qualifying aerospace hardware with a major European airplane manufacturer. So today we're going to talk about basically as a longtime user of technically immature technology, I've run into technical challenges along the way, as many manufacturing engineers do. And what I want to convey to you guys and other users like me is that working through these problems, you may have built up some bias and prejudices against the process. But I want to take a look at what Velo is doing to address those challenges and how we can deprogram those prejudices we may have against laser powder bed fusion, and what we're looking at towards the future. So, Brian, if you want to introduce yourself a little more.
Yeah, sure. Thanks, Chelsea.
The brains behind this process.
So, VELO3D was my first additive manufacturing job, which I think was kind of good because, to Chelsea's point, I didn't have a lot of these initial prejudices. I didn't have preconceptions of what could and couldn't be done. And Velo in general has had that attitude since the beginning. So I think we've worked from a very, very fresh slate, starting with the fundamental physical problems and understanding the physical problems, and then generating a software and a hardware solution around that. And that's what we're going to get into a little bit on a pretty high level today.
Yeah, so some different topics and challenges that I've ran into along the way are CAD integration. So formerly and still on many platforms, the primary software format is STL. But the engineering firms don't use STL to design their parts, they use CAD. So when you are constantly switching between file types, you are basically degrading the integrity of your file, and you run into a litany of issues with that. So Brian's going to talk about how they address that. Also, important to the process is minimizing support structures. That one's pretty obvious. And what a non-contact recoder can bring you. So as many users have probably experienced, when you have recoder contact, if your build survives, you might not get good output, but keyword being if. And also with process monitoring, so how do you know that your machine is actually producing goodness and working within the tolerances that it's meant to? And ultimately, build reporting. So engineers are busy. They're busy solving all of these technical challenges. We don't really have time to sit and do clip art and put reports together. So Brian's going to.
Sure, so I'll start with CAD integration. I think everybody here that's done a bit in AM has worked with STLs and has all their own frustrations, so I don't need to sort of dig into that anymore. What we've developed here, we started out understanding, like I said, the physical problems and quickly realized to overcome this stuff, we're going to have to write our own pre-preparation software from scratch. And so that software is called Flow, and that's our print preparation software. So it's analogous to Magix or something like this. So writing this from scratch, we have the liberty to include a lot of features that would be nice, and one of them is CAD integration. So when you work in Flow, you don't convert to STL. You import your native CAD directly, and you work with a lot of the information that was generated in that CAD. So we support native CAD formats. We support some other kernel formats like Parasolid, step files, IGES, things like this. And really, like Chelsea highlighted, when you have to go back and forth, maybe you have to jump back to CAD to make some sort of modification, whether it's to how you've added stock or you've supported or whatever you've done. The jump back and forth between Flow and CAD and your native CAD program is pretty seamless because you're not actually really changing the raw data that was in there. And when it comes back to Flow, all of your intent is still there, right?
Yeah, and something in particular I want to mention, just another thing that comes up that I don't think non-users think about is oftentimes walking around, there's all types of simulation software out there to help you improve your inputs to improve your outputs. And when you use a different simulation software than your native, you are producing maybe an inverted output that's meant to print and correct. But once you go to that file type and then you're comparing back to your CAD, it's a whole other headache. So just wanted to mention that actually addressed.
From a usability perspective, when you're doing the pre-print preparation in our Flow software, it makes things much more efficient and much easier to do. And so I have a little video just kind of tootling around a little bit with some selection, and there are things you want to do. So you want to select patches to support. You want to select patches to assign certain sub-process sets and things like this. A lot of the times, the intent that you had in CAD when you drew that particular feature, that particular surface, translates into how you want to handle it and how you want to deal with it in the print preparation software. And so, for instance, if I want to, one of the features that we have in Flow is you can take a certain surface and say, well, I don't really care if this surface is particularly rough. I don't really need a skin process on it that's going to waste time making it very smooth, because either I'm going to machine it or I don't really care about the roughness in this non-critical surface anyway. So you can select these types of patches, assign the process, and it all happens kind of in a snap, rather than inferring things from basically a soup of triangles and trying to reconstruct your surface that you generated in CAD from this mess of triangles.
Everything he's talking about now is just a nice to have in my mind. So great, looking at the future.
Yeah, I think people have talked about this for a long time, and there are some folks out here doing it now, and it's a bit refreshing. And I can tell you, I've been a bit spoiled running parts through this software compared to, I have a little bit of experience previously running through Magic and stuff, dealing with triangles, dealing with repairs and all that, and it's been much easier and much more efficient.
So minimum supports. Something that I've heard mentioned by more than one person, more than one in various meetings, is that often when talking about the business case, people tend to place little importance on supports because they don't consider it an expensive part of the process. They say, I can hire someone for X dollars an hour and they can just chisel away on the supports. I don't care as long as it runs faster. But I think that is not the right way to think about it, because when you add all of this post-processing, you are degrading your surface. You'll have residual support. You have to have the actual tooling to address those specific removal strategies. It's something that I think is overlooked in the process and not given enough emphasis. So not only if you have a part where supports can't be accessed, even if they are accessible, it's still a chore. It becomes a bottleneck, and it really it becomes a money pit within the process. So outside of the obvious reasons, there's business reasons, economic reasons behind minimizing your support. So Brian's gonna tell us how they've done that.
Yeah, I think the benefits of not having supports are pretty obvious, and Chelsea did a good job of outlining that. I'll talk kind of on a high level of how it's done. It's one of the main value propositions that VELO talks about a lot. A lot of it centers around the unique processes that we run, and a lot of those are most of the development goes into these shallow overhangs. So, and a lot of the bulk fill and a lot of other skin processes that aren't very shallow, sensitive overhangs, we do some processes that are kind of typical of other laser powder bed fusion. There's not a ton of magic in that. But in the low overhanging sensitive geometries, what you've got to do is very locally, you have to mitigate the stresses there. So you have to control your thermal gradients and control the thermal stresses that are developing in those really closely. That comes from some very unique processes. And again, like I mentioned before, we realized very early on that we were going to have to write our own software to do this. These unique novel commands are not things that you can do with other systems, with the hardware that's available or with the software that's available. And so through that and a lot of really tight process control on the machine side, we're able to achieve really high levels of control of stresses in these really sensitive areas. And the result is a lot of geometry enablement without having to support. So a lot of what my team does all day is build business cases around these types of parts where a shrouded impeller or something like this, having to load the critical flow paths with supports, it ruins the surfaces. It creates a lot of extra post-processing. and the business case quickly jumps out as being sort of ruined in a typical laser powder bed fusion system or enabled by the VELO system. So these are the kind of things that VELO really likes to focus on.
And it increases the print time. I've seen in multiple processes, even wafer honeycomb type supports, because of the way that the parameters are programmed, they actually take longer to laze than other solid metals. So not having them is just better. A non-contact recoder, the real advantage here in my mind is when you're working on qualifying parts, your customers are focused on a fixed process, which is totally fair. They want to see the same build layout printed over and over again and to produce repeatable, consistent output. And that's great, and everybody wants that. What's hard is driving at what that fixed build layout is going to look like and how quickly you can arrive at that optimized layout. So rapid prototyping isn't really rapid anymore if you have successive build failures because the recoder caught a support or an overhang that protruded too far out of the powder bed, and now you've lost your lead time. You're delaying the development process, and a rapid prototyping process isn't so rapid anymore. So for me, the huge advantage here is probably the rate at which you can get to a successful optimized build when you're going through that qualification process.
Yeah, so I'm not going to be able to get into the proprietary hardware nature of exactly how the recoder works. You're welcome to buy a Sapphire if you really want to dig into it and figure it out. But the net result is that there's no interference between the recoder mechanism and the parts themselves. So on a typical laser powder bed system, you have some sort of wiper smearing with only a layer thickness in between the part and the powder that's wiping over. And this creates, even if it's not the coder isn't contacting it, it creates some interference from the pile of powder that's being pushed across it. So I think a lot of us that have struggled with this figure out if you have a little bit of warp and a little bit of deformation and protrusion in the part, or if you have things like fine pins that tend to wick in powder from all around it and create sort of a bubble shape, a bulbous shape that protrudes a tiny bit, you have interference really easily and it starts to ruin these parts. And so a couple examples where this translates into something really useful and enables certain geometries is with the VELO system and with their non-contact recoder, there's no limit to aspect ratio that you can print. What I mean is tall, thin pins or tall, thin walls, there's no interference. So it's not going to push it. It's not going to distort it. And you can print it as high as you want. This sort of heat exchanger type geometry illustrates that pretty well. The other thing that it illustrates is there's no directional dependence. So certain edges, ledges, or thin walls, if you orient it one way on a traditional laser powder bed system, you can maybe get away with it. But as soon as you turn it the other way, you start to have a lot more interference. With a non-contact recoder system, you have very radially symmetric behaved parts. So we kind of get rid of that dependence and again, release another sort of restriction, design restriction with this recoder. One thing I glazed over quickly is, yes, the recoder is inherently more complicated, but what I kind of default to in most of these conversations is that we have a structured light scanner, and I'll talk more about it, built into the system, but every single layer, that scanner is getting real height data, not just an image, but real height data that gives you real-time data on the quality of your recoat. So you're ensured that the consistency of the amount deposited, the roughness, the plane is all consistent throughout the entire print. So you've got assurance that this inherently more complicated recoder system is actually running well. I know for a lot of people, it's a bit of a black box, obviously, and it kind of scares some people, but the assurance of consistency is there.
I'm not scared. I'm more scared of failing builds. If it works, I'm happy.
Yeah, and to Chelsea's point, I think there's a lot of behavior where I mentioned like a stick support where it just has a little bit of bulbous protrusion, or there's some processes that we've developed that have a steady state level of protrusion. They're not accumulating warp and you can print them indefinitely, but because of the melt, it actually comes up a little bit higher than the steady state of the layer. These things are now allowed because we have some wiggle room, we have some tolerance with this non-contact recoder, and it's enabled us honestly to develop some of these processes. Without it, we wouldn't have been able to work in this sort of process space. Real quickly, I know we've used it in a bit of marketing and this and that. The extreme case of non-interference, where it's really seen, is in some of the floating parts we've done. And when I say floating, I mean a part it has no supports connected to the build plate, and it itself is not connected to the build plate. So you can put it anywhere in three-dimensional space in the powder bed, and we can print just fine. there are caveats to what can be printed. It has to start from kind of a small cross-sectional area, so a point and only a single point. But what it really illustrates here, to the point of the recoder, is if you had a traditional recoder system and you could run the process in the beginning, the little bit of interference, because it's so unconstrained, would actually nudge this part away out of the way, and you pretty quickly fail your print.
I had mentioned that part of the engineer's responsibility, user's responsibility, is to make sure that your machine has the proper inputs, so you're getting the proper outputs. And on certain systems, that can be somewhat problematic. The data can be hard to attain. The sensors might not be in the right locations to get you the data that you're actually looking to analyze. So with this system, Brian will tell you, they've basically come up with a one-button solution, which I have not seen in my experience before. A lot of times the calibrations, checking your hardware, it can be a tedious process. It will involve extra equipment, it will involve sending things out. And in a manufacturing environment, in a real production environment, that can't be. You can't be waiting days to find out if your laser is running at the power and the speed that it's supposed to.
Yeah, and a lot of times when you have a cumbersome process like that, what you end up doing is putting off these calibrations, these regular checks. You don't do them often enough, and you're kind of running blind a lot of the times. And so a lot of the process monitoring is lumped into our Assure product. We launched it a couple weeks ago, and we're doing a lot of talks on it here. We've got a lot of literature on it. I'm actually giving a talk tomorrow at 2 o'clock that'll go into a lot more details. I just want to touch base on a couple important things of how we keep a consistent picture of the health of our machines and the health of our prints. So one of the things that we're looking at is basically like a pre-flight checklist, and it's checking the handful of things I have up here on the left. And as Chelsea mentioned, all of these are a user doing a one-button click, and the machine with no extra calibration plates, no special tools, will run certain commands, and we use our imaging and our sensors inside the system to collect data on it and analyze it for each of these health metrics. So I'll go through briefly on the 5 here. The thermal sensor signal here is the alignment. So we have one of our sensors is a simple coaxial thermal sensor that a lot of people are integrating in laser powder bed fusion, but assuring that that is aligned well so that you get the correct signal, and the signals that you're getting correlate to what you've done and calibrated to in the past is really important. So one button click, you get the alignment of your sensor. Beam stability. Beam stability, sometimes we'll call this thermal lensing. Really what it is if you have any degradation in your optics or any cleanliness issues with your optics, as the beam travels through, you'll start to load energy into the lenses, and you'll change your beam size at the process bed, right? Typically, this manifests in the laser window, the chamber window, accumulating soot, and it changes the index of refraction of the beam as the beam travels through it, and you lose your process, right? So what we do here basically is stress the system out with a lot of energy input and use our sensors to monitor the stability of the beam. And again, this is all one button click. This is not actionable in just the correction of a table. Usually this is a physical action. So if you have to, typically the culprit is cleaning your laser window. One thing that this metric has done for us is it's enabled us to develop a hardware solution that actually fixes that problem. So we've developed a clever way to purge our laser windows, so we don't have to clean these windows for months on end, which is much different than most systems where you're cleaning basically between every build, right? But the check is always here. So you can see if this is starting to degrade slowly over time, and it sets threshold to say, we know that our process is going to break if you have this much deflection of your beam. And so we give threshold to say, now it's time to take action on this. Laser alignment, this is positional alignment of each of the lasers. So we do full field of both of the lasers to make sure everything is actually lasing where it's commanded to, and we do overlay. And typically, if this is a little bit off, this is drifted for one reason or another, just slightly, it's just a recalibration of the galvo table. So the user presses another button to do a correction, and then they run the test again to check. And that's it. As soon as you're within the thresholds that we set for a healthy process, you're ready to run. Laser focus, same thing for each laser, full powder bed. We run and we scan all the focus. We find out a couple things. One, how close are we when we command a certain spot size to that actual spot size? And what is our minimum spot size? So sometimes you have to achieve a very fine beam. So we set a threshold for the minimum spot size that you can have. So again, one button click, you get this data all over the build plate, And if it's a little bit off, this is another thing that's a software correction, another one button click fix. And then as I'll get into a little bit more, and I talked about our 3D scanner in the system, we can get metrics of the powder bed, the health of the powder bed. So is it smooth? Is it flat? Is it consistent from layer to layer? So all these are kind of giving you a pre-flight checklist, or if you wish, you can do it at the end of the build, kind of bookend your build, make sure the machine was healthy before, and the machine was healthy after. A little more detail on the height mapper and kind of how useful it is. So again, it's a structured light scanner. It's a 3D scanner. We have a camera and a projector built into the system, and every single layer, we're getting information. We scan twice. So we scan after the layer is lased, and we scan after it's recoded. From the lased image, you can see on the bottom here, and again, this isn't just an image. This is an image on the left. This is actually the data, the height data. The colors correlate to real physical Z heights in the chamber.
Wait, more than shiny and not shiny?
Exactly. So on the next slide, I'll show you where it's not evident that there's actually an issue from the camera image, but in the real raw data, you can see that things have gone quite bad. So there's a lot of things to detect from here. So if the surface of your part for any given layer after it's being lased is quite a bit rough, then it can result in lack of fusion porosity. So it's one signal we get. Obviously, like I mentioned, we also get powder bed metrics. If your process is running out of control and you are warping too much, it comes up in this metric. We do have a limit for the tolerance of warp that the recoder can handle. This system can help, one, warn the user first if it's starting to get out of control through an email or something like that. The machine will send the user a note. And second, it can actually stop itself before it causes real damage to the system. So you don't come into chaos and a crashed recoder and ruined parts and all of this. Sort of mitigates that. So here's an example of something going wrong, right? And down here is a camera image. And what happened to this part, the V-shaped symbol, is it actually snapped off the build plate. When it snapped off the build plate, the part itself wasn't protruding much, but it threw a bunch of powder everywhere, right? And so if we would laze on top of this, it would cause lack of fusion. It could cause delamination. It cause a bunch of issues.
I've heard this called the tuning fork effect, where it hits it and it rings,
exactly.
It rings and it flings powder.
Exactly. And you can see kind of something's going on in this image, but you can't really infer what was going on. As soon as I looked at the height map and I saw the powder surrounding the part and I saw the actual real physical level of the corner of the part, I knew exactly what had happened. It had snapped. It hadn't actually moved the part much, but it had thrown powder everywhere. In the case of this build, I did a recode, it smoothed the powder out, and we just continued. No problem. That part's actually sitting in one of these cases right now. But if the part was really protruding because it snapped and it was up too high, or if it was warping because you're accumulating too much stress in a sensitive area, it's evident on this and exactly what's happening. So it's a really good troubleshooting tool, and it's a really good continuous health metric that you get every single layer throughout the build.
And you don't have a failed build.
Exactly. The parts actually made it out. We don't have to ruin this print just because we don't understand what's going on here. We got a lot of insight on what's going on.
So build reporting, like I talked about, we engineers are busy overcoming technical challenges day by day. And so the last thing that I've had time to do is compile the data, hoping that it's good data, not garbage in, garbage out. And basically put it in a format that I can share with my customer to assure them that what I'm giving them is actually of quality and a good integrity part. So having the capability to do that simply and efficiently is really important to me.
So this is another thing that's included in the Assure product. There's a lot more details behind this. I just want to kind of on a high level give you a bit of an overview of what it does. So basically, the idea of this build report, Chelsea mentioned, is after your build is done, it's a one-button click, and the Assure software spits out a PDF at you. And it has a lot of information. I'll go through a little bit of what it has. There are also example build reports, literature around here, so you're welcome to take one before you leave the booth. It starts with basic build statistics. So what is the name of the build? What is the software revision that was used? The preprint software revision that was used, and the machine software revision that was used. What are the parts called? How are they arranged? How are they laid out? How long is the build supposed to take? Are there interrupts during the build, right? Did you have some sort of anomaly that stopped the machine and you had some sort of pause? Something that is really critical in AM to make sure that you monitor, but not always tracked. It can be easily missed if somebody isn't there constantly watching and logging what's going on with the machine.
And even times it can be a bad practice to rely on your operators to remember to tell you that something happened. They probably will if you're standing there, but if you're not standing there and you don't ask, it might not ever happen. So it takes that responsibility off of the operator. off of the engineer, and you can easily see what's happened in the build.
Yeah, so this is, again, using the same build where I showed the protrusion. What we see here is exactly what layer, exactly what time, how long the machine was actually paused, and the reason. Excuse the cryptic signals that we're getting here. But basically, this is telling me that the height mapper counted a lot of protrusion in this layer, in this time. And so after a few hours, somebody came in, or like I said, I recoded, it was fine, and I continued to print. But you have a log of every one of these interrupts going on in the build. Another thing that's pretty straightforward are the some of the basic sensors that run on the machine. So if you want to monitor oxygen levels and pressures over the filters, pressures in the chamber, this is all configurable by the user. And there's tons of sensors that go into the machine. You get heat maps and you get flags. So the yellow flags up there are saying something is getting close to a threshold that might be wrong, and then we flag red if something actually goes out of spec. And then you also get strip charts, right? So you can see this really in time over layers or over time. How is this metric progressing every single layer or per unit time? Another thing that I'm not going to go into detail here that you can throw into this is our defectivity probability metric in Assure, and I'll be talking about a lot more on that tomorrow. Height mapper data is also wrapped into this. So if you had events that cause some sort of protrusions, or even if it's getting close to the threshold, you can have that in this report. And also in the Assure product, you can go back every single layer, all this data is saved, and look at these height maps and try to figure out if you have something wrong, or if you just want to understand, you didn't have time to watch the entire build, but you want to understand how this build is progressing throughout. So that's it. I'm going to be around all day, obviously, if you guys have any other questions, but thanks for joining, and thank you, Chelsea.
Thanks.